How you doing, Benny? Surprised you're here.
All right, so I believe we are still on page 104. Is that correct? We need to finish the rest of that chart. Did we do the bottom two questions? With the tangent and the normal? We did those? Did we draw the graph of h of x?
Yes. Yes.
Oh, no, we didn't. We did the points.
We did the points. We started to, I think. Okay, so on page 104, we were given the graph of the derivative, aka slope, and we were able to analyze this derivative graph to determine where the original function, okay, h of x, was increasing, decreasing, where it had a max, where it had a min. So using these different characteristics that we were able to find, let's go ahead and try to draw a rough sketch of what the original function would look like. Okay, it's just a basic picture. We're not really sure where specific points are. Okay, we'll get to that point eventually, but this will just be a rough idea. So we're specifically looking at locations of 1, 3, and -2 in terms of our maxes or mins. We don't know exactly where the point is at the x location of 1, but we do know that it has to be a maximum. So wherever we put that point at the x value of 1 needs to be higher than where we put the x or the points at the x values of -2 and 3. So I'm just going to put points at those locations. I know this has to be a maximum and the other two are minimums, aka low points. And we're going to kind of play connect the dots in a way that we are specifically increasing on these intervals and specifically decreasing on those intervals. So if you were to draw your graph from left to right, notice how you begin with the location of -infinity, and you should be decreasing all the way to -2. So from left to right, decreasing, you can kind of anticipate that shape. Ready? Okay. You can use a calculator. Okay. Just pick a seat. Okay. All right, if we look at our next two dots, we have to connect from -2 to 1. That fits this interval, and we should be increasing. So we're only going to increase or connect those dots in an upward motion. We don't have any crazy squiggles going on in between them because these are the only maximums and minimums that we identified. To connect the next two dots from 1 to 3, we have to be decreasing. So we're only going to draw a graph going down. Again, nothing crazy in between those 2 points. And then after 3, all the way to the right, we should be increasing. So we're going to go back up. So this is a rough sketch about what the h of x graph might look like. Does that make sense? Using those characteristics that we identified? Okay. Do we remember the connection between the equations of the original graph and the derivative graph? For instance, with this derivative graph, can you tell me the name of the function based off the way the graph looks? That kind of curly S shape, what name of function looks like that? Yeah?
Might be a third, but it also might be a fifth.
It could be a fifth. We're not really sure, but we're going to go ahead and say that it's cubic. Okay, that curly S shape is typically identifying a cubic graph. So if the derivative is cubic, aka a degree or power of 3, then what must the original graph have been? Do we remember the connection? Yeah.
Quartic.
Quartic. Okay, it's one more degree. And quartic graphs kind of look like W's. And notice how this one kind of fits that W-like shape. So h of x should be quartic, and it makes sense based off the graph that we roughly drew. Okay, we're going to analyze this relationship a little bit more today. Notice how the derivative is 1 less power than the original function. Okay? Anything else from that section that you guys want to go over? You guys are really going to like today. I promise. Really, really. Okay? So our next section, starting on page 109, we're going to look at derivatives even further, but this time we're going to talk about some shortcuts. Okay, so up to this point, what has been the only method or technique that we have used to find the derivative algebraically, okay, by hand? I know graphically we were able to draw a tangent line and kind of estimate the slope. But how did we find derivatives by hand? Yeah. You use the limit. Okay. Do we remember what that limit looked like? Very, very important. What is our sole limit that gives us a derivative? What are we approaching? What does the function part look like? What's our limit definition of a derivative? What do you think, Braden?
F of x plus h minus f of x.
Yep.
All over h.
All over h. Good.
H is approaching 0.
H is approaching 0, okay? The limit definition of a derivative is basically slope. The slope of a secant line. Notice how you have y values being subtracted up top over x values that were being subtracted on the bottom, but we eventually saw that those x's canceled out. Okay, this is the only way that we've been finding derivatives so far. And I think you would agree with me that it's been kind of a tedious process. Some are easier than others, okay, but this is the only method that we have done so far. So in terms of derivative shortcuts, we're going to try to simplify this process by trying to look for some patterns. Okay, if we were to use this limit definition over and over and over and over again, maybe we can draw some connections. That way we don't have to do this every single time. Okay, that's what we're going to look at today. So let's first take a look at something simple here. F of x equals 3. That's a constant function. Your function is just a number. What would that graph look like? The graph of a constant? Yeah.
Just a horizontal line.
Horizontal line, and specifically this one would be at 3. So somewhere above the x-axis. Okay. If I were to draw a tangent line at any x value, what would that slope be? Okay, so I'm going to pick any point I want. And drawing a tangent line on a constant function is a little tricky because you're essentially on top of that constant function. Okay, tangent lines never ever go up or down. Why do you think that is? What's the slope of a vertical line? Yeah.
Undefined.
It's undefined. Okay, so tangent lines never ever go up or down. We only have tangent lines that are angled or tangent lines that are flat. Okay, so we're actually going to get into that later this year. That's a big idea. But if I were to draw a tangent line at any point on this constant function, what would the slope of those tangent lines be? The slope of a flat line? Yeah. 0. Okay, so we can say for a constant function, the derivative, aka slope at any tangent point, is always 0. Okay. Mathematically, we can show that using some notation. Okay, the derivative, aka f prime of x, would always equal 0. So that's one nice shortcut for us. If our function is just a number, instead of having to go through a limit definition to help us find the derivative, we simply know that the derivative is always 0. Okay, nice shortcut. What I'm going to do here in this table is I'm going to go ahead and show you, write down what the derivatives are. And I want you to pay close attention to what they kind of look like in relation to the original function we started with. So I'm going to do the first 3, and then we're going to try to find a pattern for us to use, and we'll apply that pattern to the last 3. Okay? So if I were to use this limit definition of a derivative on this function, this is what I would get. If you could imagine substituting in x plus h for all those x's, subtracting the original function, dividing h, expanding all those parentheses, canceling everything out in terms of like terms, canceling out all the h's that would go away, this is what you would have, okay, if you were to use that limit definition. If I were to use the limit definition on the next one, this is what the derivative would look like. And if I were to use the limit definition on the next one, this is what my derivative equation would look like. So with those 3, can you find a pattern? Can you take a look at what you started with in the original function and what the derivative, aka slope equation at any point looks like? What do you see, Dan?
In all of the previous ones, you would take the exponent of number. So, for example, fx equals 3x squared minus 2x plus 3. You take the x degree, so 2 times 3 would give you 6x.
Okay.
And for the negative 2, it would be negative 2 times 1 would give you negative 2. And since the 3 plus 3 has a x0 degree,
Okay.
technically speaking, then you would get nothing. The bottom one also does the same thing. Negative 5 times 3 is 15.
Yep.
2 times 2 is 4. And negative 3 times 1 is negative 3. And the 1 would get canceled out because of that 0.
Perfect. Were we able to follow that, what he was saying? Maybe, maybe not. Okay. He's completely right. We have one other thing to add to what he was saying. So notice how this power of 2, if we were to multiply it down to the coefficient of 3, wouldn't we get 6? Right? Now what's happening is Dan noticed that connection by taking the power times the coefficient. But what happens is whenever you move that power down, your new power is 1 less than what you originally had. And didn't we say that was kind of a connection between the original and the derivative? On the graphs we just drew, didn't we have a quartic original but a cubic derivative? Okay, you have 1 less power, so you've got to subtract 1. Dan mentioned this one a little bit differently. Notice how there's no x on the 3, so technically you can think about that as an x to the 0 power. If you brought the 0 down, 3 times 0 would be 0. So you're not really left with anything. Another way you can look at it is this 3 or this 1, isn't that a constant function? It's just a constant value. And the derivative of any constant we said was 0. So you don't have to write it if you don't want to. Technically there should be a plus 0 there to represent the slope of 3, but you don't have to write it because adding 0 doesn't change anything. Okay, so what we're doing is we're just working through each term individually. We're taking the power on the x times the coefficient out front, and we subtract 1 from that original power for every single term. Okay, let's go ahead and see if we can use this pattern or shortcut for the next 3. Okay, they get a little bit more involved because now we have negative exponents or fractional exponents. Let's take a look at the first one. If you were to take the power of -1 and multiply it down to the coefficient of -2, that would end up being a positive 2, and you have to subtract 1 from that original power, which means your new power was negative 2. If we continue through, power of negative 2 times coefficient of 3 would give us a coefficient of negative 6, and subtract 1 from the power would give us a negative 3. There's your derivative. Instead of having to go through that whole limit process, we've developed this shortcut or pattern. I'm sure you guys like that better than using those limits. Yeah, okay. Can you guys try the next two? Give them a shot. I know they're fractions, but we can work with fractions. How do we do with those derivatives? Pretty good? All right, so this shortcut that we're developing here by multiplying down the power and then subtracting 1 from the power has a special name. Okay, we're eventually going to talk about some other derivative shortcuts that are going to have names as well. So you're going to hear me call them by name. Okay, that way it's a little bit shorter than just describing the process. This is what's called the power rule for differentiation. Differentiation just means finding the derivative. Okay, and again, it's called the power rule because we are manipulating the powers. Okay, we are multiplying down the power and then subtracting 1. Okay, power rule. So in general, we're going to write what this power rule looks like, okay, for any type of x to a power representation. Now, there's a little bit of notation here that we haven't seen yet, and we'll get to that eventually. This notation of d over dx is telling you to take the derivative or find the derivative. So we're specifically going to take or find the derivative of this x to the n function. So can we write this power rule in this general term? If you had x to the n, what would the derivative look like? What do you think, Allison? Okay, so we got to subtract 1 from the power. That's part of it. Where does this power go? Let's see. For instance, this negative 1 became a negative 2, but there was something else we had to do with that negative 1. Yeah?
Multiply the coefficient.
Multiply the coefficient. Now, in this case, the coefficient out front is just 1 because you don't really have anything over there. So if you were to multiply down that n, we would have an n out front. So n is your coefficient times x to the n minus 1 after you subtract 1 from the power. Okay, so in general terms, that's what this power rule looks like. All right, we're going to spend a lot of our time practicing, though, this power rule because the ones we did on the chart were kind of simple, but not every equation or function that we're given is going to look like those simple ones. We might have to manipulate them a little bit in order to use the power rule. So this is when we're going to talk about polynomial form. Polynomials are those nice curvy looking graphs like x to the fourth, x to the fifth, x to the third, quadratics, all those nice ones, okay? But a polynomial form always has some x to the n power, and you might be adding or subtracting some other x powers in the equation. And sometimes there's a constant on the end. For instance, we can have an x to the fourth plus an x to the third minus an x squared. Maybe we're adding 1 on the end, something like that. Okay, but a polynomial form is simply put as having x to some powers. No parentheses, no fractions. Okay, we have simply x to some power all the way through our equation. So in order to use the power rule, you have to have a polynomial form equation. And we're going to practice turning these other equations into polynomial form. That way we can use the power rule to help us find the derivative. Okay, so take a look at our first one here. We want to rewrite this so we have x to some powers all the way through. Okay, no fractions, no parentheses, nothing like that. So how might we be able to write 2 over x squared, because right now that's a fraction. How might we be able to write that in a polynomial form? How can we get this to be x to some power? Yeah?
You can multiply it by x over 2 and get rid of the fraction as well as distribute to 4x over 3.
Well, if you multiply this side by something, you're going to have to multiply this side by something. Okay? Notice how your x is located in the bottom of a fraction, right? Can we move that x to the top of the fraction? Wouldn't that get rid of the fraction if we move it? Yeah. There we go. Okay, so we're going to utilize some negative exponents. You can move a variable to the top by switching the sign on the power. Okay. Now, if you look at the next term that's already in polynomial form, it already has x to some power in it. So you don't have to change that one at all. Okay, notice how we have x to some powers with some numbers out front. Those are fine. But we always need x to some power. No fractions, no parentheses, nothing else. Okay, so if this is how we can rewrite the original equation in polynomial form, let's go ahead and apply our power rule to find the derivative. A little shortcut for us. What would our derivative look like? Can we apply the power rule? Anybody want to give it a shot? Multiply down the power, subtract 1 from the power. What do you think, Braden?
Negative 4x to the negative third
Yep.
minus 12x squared.
Minus 12x squared. How'd you guys do? Pretty good? All right. Now here's the thing. That is a wonderful derivative to find using our shortcut. But in terms of like test-taking strategies, because we know how the AP test is multiple choice and free response, this might not be the way the multiple choice answer is written. So we have to be a little strategic and think about, are there other ways we can rewrite the way this derivative looks? Okay, so we're going to practice rewriting these with no negative exponents. Maybe we can combine them into one fraction when possible. So we're going to see where we can go with this. This is perfect. Okay, this is a correct derivative. But we need to practice rewriting it just in case our solution doesn't match something like parts A, B, C, or D on a multiple choice question. So notice how we do have a negative power. We can move that back down to the denominator of only that term. So it'd become a positive 3. and we'd have a minus x squared on the end. Maybe that's the way the response or the answer looks like on a multiple choice test. Okay, we could take it a little further. Can we combine those two terms together? Notice how we're subtracting them and one of them's a fraction. Can we get a common denominator so that we can subtract the numerators? Notice how we'd have to multiply the second term by an x cubed up top and on the bottom. And if we multiply the top by an x cubed, we would now have an x to the 5th. And that new common denominator would be an x cubed. So all of these are the same derivative. They're just represented in different forms. Okay, so I would say any of these three are perfect, but since the directions are telling us no negative powers and write your answer as a single fraction when possible, okay, we'll take this one as our final one. All right. You guys are going to get really good this year of taking derivatives. I promise. The hardest thing that's going to kind of cripple us in some cases are rewriting. Okay, simple algebraic techniques. The calculus is going to be great. The algebra is our weak point for some of us. Okay, let's go ahead and try the next one. Can we rewrite this in polynomial form? Okay, no fractions, no parentheses. Stevie, can you do me a favor and shut the door? What do you think, Vinny?
3x to the third minus 3x.
Perfect. How'd you get that?
Just divided x out.
Divided the x out. Okay, so you can factor an x out of everything up top. It would cancel out with the x down below. I think we mentioned how this is a single term denominator. STD, if you want to look at it that way. You can divide each numerator quantity by the single term denominator. Notice how when we do that, we have a polynomial. We have x's to powers all the way through. So based off of that polynomial, let's go ahead and use our power rule to find the derivative. If you were to go through that tedious limit process, what would you eventually get? Any takers? This is a nice one now. Yeah. 9x squared.
Oh,
Yep.
yeah. Minus square
Minus 3. Perfect. Okay, the derivative of a constant on the end is 0, so you don't need to worry about that. No negative exponents and no fractions that we have to combine, so we can just leave our derivative that way. All right, let's try the next one. Not exactly in polynomial form right now because we have parentheses. We want to get rid of those, so we might have to go through some distribution process. Maybe we'll multiply the first two groups together. We'll have x squared plus 2x plus 3x, but that would leave us with 5x, and then plus 6. So kind of go through a FOIL process with your first two factors. But now we have to go through a distribution again with these two factors we have left. Do we know how to do these types of distributions? You have to just bring in every single term, distribute every single one in individually. So x squared times 2x, we got 2x cubed. X squared times 1 is x squared. Do the same thing with the 5x and the 6. Alright, so there's our polynomial. That's representing the original function. Okay, we haven't done any derivative yet. So if you were to find the derivative, what would your f prime equation look like? Can we apply the power rule? If you were to use the limit for a derivative on that crazy thing, what would you eventually get? Ryan, do you want to give this one a shot?
6x squared plus 22x plus 7.
Good. How'd you guys do? Good? All right. No negative exponents, no fractions to combine, so we'll just leave it like that. All right, let's try the next one. Not exactly in polynomial form yet. Can we get it to look like a polynomial? X to some powers all the way through? Let's see, we have another single term denominator, so you can divide each one individually. We would have x, let's see, we would have 2 x's left in the denominator, but that would still be a fraction. We could move those 2 x's up top as a negative exponent. And kind of the same thing happening with the next term. We would have 3 x's left in the denominator, but we can move those up as a negative power. So now that we have a polynomial, we have x's to some powers. What might our derivative look like using our power rule? Let's see, we'll have negative 2x to the negative third plus 15x to the negative fourth. Is that what you guys initially have? Okay, but we could possibly rewrite this. We don't want any negative powers, so we can move the x to the third to the denominator of its term, and we can move the x to the fourth to the denominator in its respective term. So that's another way it might show up perhaps on a multiple choice question. Can we add fractions together? We can represent it another way. To get a common denominator, we would need another x in the first fraction. Multiply an x up top and down below. That way it would match the x to the fourth. So if I multiply the top by x, I'd have negative 2x and then plus the 15. Okay, so all 3 of these are different ways the derivative can be represented, but they all mean the same thing. We doing okay? Do we like the power rule? A lot better than the limits, right? I tend to think so. All right, let's go ahead and step it up a bit. Are we familiar with how to rewrite roots? For instance, the cube root of x squared. No, we're going to get good with this. Okay, so maybe off to the side we'll write these down. The square root of x can be rewritten as x to the 1/2. Remember, the power rule is all contingent on a power, because you have to bring down that power and then subtract 1 from it. So we want to make sure we can rewrite different quantities or representations as powers. If we have a cube root of x, that's the same thing as x to the 1/3. If you continue that pattern, the 4th root would be 1/4, the 5th root would be 1/5, all that good stuff. Okay. Sometimes, though, we have a power on the x, kind of inside that radical symbol. In these 2 examples, the powers on the x's were 1s, just x to the first. So if we kind of use that connection here, we would need an x to the 2/3 power. Okay, it's going to be a fractional exponent. So whenever you have a fractional exponent, it's representing some type of root. The denominator of that fraction is the root you have, either a square root or a cube root. and then the numerator is representing the power on the inside quantity. Okay? So we can rewrite the cube root of x squared as x to the 2/3 power. Can we continue to rewrite that? Because we need a polynomial form. We need x to some power. Right now we have a fraction. If you have an x to the first divided by an x to the 2/3, can we somehow use some exponential or exponent properties to help us get rid of that division? When you're dividing the bases, what do you do to the powers? You subtract them. I heard it. Okay, so 1 minus 2/3 would give us a new power of 1/3. Notice how we have a polynomial. We have an x to a power. So let's go ahead and find the derivative using our power rule. Let's see, if I bring the 1/3 down, times the 3 would give me a 1 coefficient. And if I subtract 1 from the power, that'd be a negative 2/3. Right? We have a negative power, so we can change it to a positive power by moving it to the denominator of a fraction. Can we change this back into a root, just in case it would look like that? X to the 2/3. What would the root be? What would the power be? Can you tell based off of the 2/3 fraction?
Hello? Yes. Sure, no problem. Yep.
All right, can we rewrite x to 2/3 as a root? What do you think? Good, Braden?
Cube root of x squared.
There we go. Cube root. Okay, that's the denominator. Cube root. And then whatever's inside the root itself is being squared. So all three of these are correct derivatives. They just look different. All right. Can you guys try the next one? A few more fractional exponents. Let's see, I think this one's already in polynomial form, right? No fractions, no parentheses. So go ahead and use your power rule. All right, how do we do on the initial derivative using the power rule? Pretty good? Okay, we're going to practice cleaning it up, okay, rewriting it. Notice how we have some negative powers, so you can move them to the denominator of a fraction. You already have a 2 in the denominator of the 1/2 coefficient, so you can just move the x down with that. Are we okay with moving the x's? Okay. Can we add these two fractions together? Can we get a common denominator somehow? A little tricky because now we're dealing with fractional powers. Let's see. Don't we definitely have to multiply the first fraction at least by 2 on top and bottom? Because this one has a 2. Okay? And what do we have to multiply x to the 1/4 by to get an x to the 3/4? This is the question. Let's see. X to the 1/4 times x to what power would give you x to the 3/4? When you multiply the bases, what do you do to the powers? You add them, okay? So 1/4 plus what would give you 3/4? Yeah. 2/4, aka a half. Okay, so we have to multiply this first fraction by 2 on top and bottom, so that would change the -3 to a -6, but also by an x to the 1/2. So that's going to change our first numerator. We'll add the 1 from the second numerator in the fraction, and we'll have the new common denominator of 2x to the 3/4. Alright, so we have 3 representations now of what the derivative might look like. We do have fractional exponents. Can we turn those into roots? What would it look like if we wrote it with roots? X to the 1/2 is the same as, let's see, we said the square root of x. And then we have plus 1 all over 2 times, what would x to the 3/4 look like as a root? What type of root do we have, and what's the power on the x? What do we think? 4th root, x to the 3rd? Yeah? Alright, all 4 of those are the same derivative. They just look different each time. Okay? How are we doing with the power rule? Power rule is going to be good. It's the rewriting that's going to take some practice. Okay? We're going to do more with the power rule tomorrow, maybe in terms of some trig functions. So we're going to get a little triggy on you, but I think it's nothing that we can't handle, alright? David, what's up?
Hi.
Hi. What do you need?
I think Vincent
Vinny,
should
yeah.
have explained everything.
Miss Lenz is the one that called.